In the previous lecture, we started a discussion on solid state RF devices and in particular diodes. And while discussion, we mentioned that the standard PN diode which we use for our basic circuits applications is not good enough for RF circuits, primarily because in the reverse bias, it behaves pretty much like a decent conductor because of its very high capacitance in the junction or the depletion region. So to overcome this capacitance problem, we took a look at what is called as the pin diode. That is the P, then the intrinsic and followed by the N layer. And we saw how it can be used as a switch to either send or not send an RF signal, and that on and off phenomena of the switch is the on and off condition of the switch is controlled by an external DC voltage. We took a look at a single pole switch. So what that was a single pole single throw switch. Now, one of the drawbacks of the pin diode is the fact that its depletion region is wider, or rather it's thicker. So while it is indeed able to act like a good insulator in the off condition, the problem is that the depletion region is able to store a lot of charges, and therefore the diode takes some time to properly switch on, and that is what is called as the reverse recovery time, or the time taken by those stored charges to essentially recombine and die out. So that is called as the reverse recovery time. So that is high for pin diodes. Now, what happens essentially is that if you are looking for a diode with pretty low reverse recovery time, and at the same time, if you are looking for a diode which can respond to weak signals. Now, when I say weak signal, it means the signal whose amplitude is on the lower side. Now, suppose I have a normal PN diode and I have a pin diode. So each of these diodes, they have something called as a V gamma, and this V gamma is nothing but the built-in potential. So generally for silicon diodes, this V gamma is in the range of 0.6 to around 0.85 volts. What this means is, if you want to turn the diodes on just by the virtue of the signal itself, that is like saying, if either of this, if I have an RF signal and I want to connect it to either a PN diode or a pin diode, this input, let us say V in, must be more than 0.6 to 0.85, or this V gamma of the diode, to properly turn it on. So if this is what we call as the load voltage VL, you will see that VL will always be equal to V in minus V gamma in the on state. So therefore, any signals whose magnitudes are below this V gamma will be unable to turn these diodes on. So therefore, if you want to use the diode to respond to weak signals, then neither the PN diode nor the PIN diode are good candidates. So to avoid this drawback, if you are looking for a diode with lower built-in potential, what can you do? So as you know, the built-in potential V gamma is effectively kT by Q ln of Na times Nd divided by Ni square, where Na and Nd are the donor and acceptor ion concentrations in the P and N sides, and Ni is the intrinsic carrier concentration. K is Boltzmann constant, T is temperature, and Q is the electronic charge. So one of the things that we can do is to change the material, and the material will essentially change these concentrations. So one of the semiconductor materials which can be used to make diodes and is of a lower and can also offer a lower built-in potential is germanium. But essentially germanium again suffers from the same problem as that of a PN diode. That is, it's the germanium diodes that are available are usually quite poor conductors, or rather actually they act as poor insulators when in reverse bias. So therefore, no matter how much you change the device parameters, often the standard devices or the diodes cannot be used at RF frequencies. So this problem was essentially solved by a scientist, and he gave rise to what is called as a Schottky diode. And this diode is rightly named after him. So he said that I'll make a very simple change in the existing diode. That is, this will have two terminals and two layers. One of the layers is an N-type semiconductor, but the first layer is a metal. So effectively it is a junction between a metal and an N-type semiconductor layer, where this is the anode and this is the cathode. The symbol for the Schottky diode is something like this. It looks like a rectangular form of S. Don't confuse this with the Zener diode. The Zener diode symbol is something like this. This is Zener. The Zener and Schottky are not the same. So this is what the Schottky diode looks like in the form of a symbol. Now the question is, what is the advantage that is offered by the Schottky diode? What is the advantage that is offered by the Schottky diode? Now what happens is, because of this metal and semiconductor junction, there is no concept of anything called a depletion layer. The depletion layer is almost negligible in this case. So therefore, smaller the depletion region, lesser will be the number of stored charges. So therefore, this can turn on and off very fast. Turns off on and off very fast as compared to either the PN diode or the PIN diode, because the depletion region is very, very small. The other advantage of the Schottky diode is that because this is a metallic layer, the built-in potential or the V gamma is comparatively lower. because this is already a conducting layer. So if the V gamma for the silicon diode is in this range, the V gamma for the Schottky diode is even lower. So modern day Schottky diodes can give you anywhere from 0.15 to around 0.4 volts, which is much lower as compared to the silicon diode. So this is low V gamma, which is also an advantage because this can then respond to signals of weaker magnitude. So the question is then, if the Schottky diode provides us with two major advantages. One is that it can switch on and off very fast with respect to the signal, and also the fact that it has much lower built-in potential, then why not use the Schottky diode everywhere? Well, we don't use that everywhere because, like everything else, the Schottky diode also has a drawback. The drawback is that the way it behaves when it is in the reverse bias. Now, for a normal diode, for the ordinary diode or a normal diode, the diode equation is essentially governed by Shockley's equation. The diode current is essentially governed by Shockley's equation. So, if you recall, the diode current is essentially Is times e raised to Vd by eta times Vt minus 1, where Vt is Kt by Q. So over here, when you draw the IV curve for a normal diode, effectively what happens is that it looks like this. Where this Is is what is called as the reverse saturation current. So when the Vd is much below Vt or much below V gamma, there a very small current essentially flows over here, and this one, because of the nature of the equation, is almost a constant. And this magnitude is essentially Is, because it is actually flowing in the reverse bias. Therefore Is is occupying the third quadrant. Now what happens is, this Is is essentially the current that is contributed by the minority carriers. Is is the current that is contributed by the minority carriers. That is, in the reverse bias, when there are no free charges or free majority carriers, it is the minority carriers in the P and N semiconductors which try to flow, but their magnitude is very small, their concentration is very small. So therefore this Is essentially contributes to that current. So this is what is called as the reverse saturation current. So for most diodes, this is of the order of, a few nanoamperes at the very most. For Schottky diodes, unfortunately, this Is is much larger because one of the layers is metal. So a metal has always more free charge carriers available. So therefore for Schottky diodes, what essentially happens is that this has a much larger value. So here you can see that the V gamma is little larger, here the V gamma is little smaller, but the Is is now higher. This is the problem. So the reverse saturation current for Schottky is much more than that for a PN diode, and that is more than that of a pin diode. Because here the depletion region plays a very important role in keeping the saturation current low. However, as we discussed, in terms of the reverse recovery time, the TRR for Schottky is the lowest. This is what it is. So the question is, where can we use Schottky diodes? We can use Schottky diodes in those areas where we essentially have to respond to weak signals. Now let me give you a very exciting application. In recent years, because of the demand for sustained energy sources, many scientists are working on something called as RF energy harvesting. So essentially, RF energy harvesting refers to a broad field where we can use the additional ambient RF energy that is all around us. Wherever we are, mostly whether it's outside or inside, there are RF signals all around us. Maybe from a mobile tower, maybe from a Wi-Fi router, or much more than that. So the question is, can we somehow use a small part of this power for some good use? That is, can we power a small circuit using that? Now, what is important to note is that the RF signals around us usually are of medium to low magnitude. So we need to capture them properly. Then we need to convert them into a DC voltage so that it can power any small circuit. Or let us say it can charge a very small battery. Obviously, running high power applications this way is quite challenging, but there is a lot of research that is going on into seeing whether low power devices with good efficiency can be run. So therefore, what essentially happens is that we need to capture ambient RF and then convert it into DC. Because DC can power small circuits. So to capture the ambient RF, we will need an antenna. And to convert it into DC, we will need an AC to DC converter, because the RF signals are alternating in nature. So AC to DC converter is also called as a rectifier. So the rectifier plus antenna configuration, if you add these two, the name is called as rectenna. Now, a very simple example of a rectenna is when you have an antenna and you don't actually have a rectifier, but you add a rectifier with components that can convert the rectified signal into DC. And which components can convert the rectified signal into DC? That is capacitor, because once you charge them and don't give them an easy path for discharging, then they will definitely be able to hold on to that value or the magnitude peak of those rectified signals. So if I have an antenna, it is able to receive RF signals. So then what will happen is that you will have to combine a rectifier with those capacitors, and therein we have a very nice circuit that is called as a voltage doubler. You may have already come across the voltage doubler in your basic analog circuits course, and it looks just like this, except the diodes are now replaced with Shocky diodes. So this is what is called as a voltage doubler. Now a voltage doubler, what it does ideally is that if the signal that you're receiving is of the order has a magnitude of V0, then ideally the load voltage, it will be of a magnitude 2V0 in DC. This is how a voltage doubler works. So you have a C1, you have a diode D1, you have a diode D2 and a capacitor C2. So you will probably already be familiar with the way this works. That is, in the negative half cycle, this diode essentially conducts and charges up the capacitor C1. It charges up the capacitor C1 to ideally V0, if you assume that these two are ideal diodes. So what happens is that once the positive half cycle starts, this capacitor almost behaves like a source for this capacitor. So the V0 plus the V0 of the positive half makes this capacitor charge through diode D2 to a maximum value of 2V0 ideal. So what we essentially have is this. The load voltage, that's equal to 2V0 in case of ideal diodes. But in case of a Schottky diode, it will be 2V0 minus 2V gamma. So if you assume that V gamma is 0.15 volts and let us say V0 is 5 volts, let us say. If V0 is 5 volts, then what we expect ideally is 10 volts. Over here, with the Schottky, you will get something like 10 minus 0.3, that is 9.7 volts, which is very, very close to the ideal. But if you use a normal pin diode or a PN diode, what you will get is 2V0 minus 2V gamma. If you assume that V gamma over here is, let's say, 0.7 volts, so what you will get is essentially 10 minus 1.4, which is about 8.6 volts, which is quite away from the ideal expected voltage of 10 volts. Lower than the Schottky diode. So this is a very interesting example of the Schottky diode, which can respond to signals, in particular RF signals of very low magnitude. Now, let's go back a little bit to the previous lecture and talk about the quantity which we briefly discussed. The quantity that makes the ordinary PN diode unsuitable for RF applications. And that quantity is called as the junction capacitance. The junction capacitance Cj. Now what we saw was that this junction capacitance Cj depends on a number of factors. One of them was the width of the depletion region, XD, and the fact that XD changes when the reverse bias voltage is changed. So we saw that this Cj is essentially proportional to 1 by XD. Now let us say if the reverse voltage is VR, if the reverse bias voltage is VR, then as VR increases, then the depletion width will become more and more. So therefore even XD will increase. So when XD increases, the junction capacitance essentially reduces. So in general, what happens for a normal diode is that if you draw a plot of Cj versus VR, you will observe something like this. Right? So when the VR is least, the XD is minimum and the capacitance therefore is maximum. As VR increases, the XD increases, so therefore capacitance reduces. So here, when VR is minimum versus when VR is maximum, after a while this may become flat. So if you now join this over here, let us call this as C max and this as C min. We define something called as the junction capacitance ratio. And this is CR, which is C max by C min. So why am I talking about this capacitance ratio? What we are essentially seeing is that when we are changing the reverse bias voltage, the capacitance of a diode is changing. So therefore, this opens to us a whole new range of possibilities. That is like saying, by simply changing the voltage across the diode, the reverse voltage across the diode, I can change capacitance. So I can actually offer myself using this a variable capacitor. Possibility of a variable capacitor. So think how good that would be if we were to use them in impedance matching, if we were to use them in an L match network. Just by changing the capacitance value, I can change the frequency of matching. Or if I were to have resonance in an RLC network, I can change the capacitance value and change the resonance frequency. That gives me flexibility as a designer to use the diode as a variable capacitor and not limit the performance of the circuit. Now, when we look at the junction capacitance of a PN diode, a standard PN diode, we will notice some problems. First of all, this CR is quite low for most diodes. Why it is low? It is low because of the doping profile. A doping profile means with respect to the distance, what is the doping concentration? So if this is a PN junction diode, now if this I label as the x-axis and this is the concentration of the ions or the carriers which are being doped as a function of x. So let us say the doping concentration in the p side, that is the acceptor ions, is Na, and in the N side the doping concentration is Nd. What you will see for a normal PN diode is that for this entire distance, the doping concentration for the whole length is kept at a constant Na. Now the moment it touches the junction, the concentration changes and it becomes Nd. This kind of junction is called a sudden step junction because you have uniform, then you have a step, and then again uniform. So this is called as a step graded junction. This is called as a step graded junction. This is what happens for most PN diodes. There are other kinds of doping profiles also which result in different junctions. I'll tell you one more example. And that is what is called as a linearly graded junction. Wherein again you have a PN, but the doping is essentially done in a little different way. So suppose initially the starting doping concentration over here is Na, here it is Nd. So here we start with Na, and as we come close to the junction, what we do is that we start changing the doping profile right away and we move towards N, but in a more gentle way. And then again, once we hit this Nd, we make it fixed. This is called as a linearly graded junction. These kind of junctions you will find in the collector base junction of a transistor. Of a BJT. Right? So anyway, we will not go very deep into the junction description. I'm just giving you an example. Now the point is, if you were to plot Cj versus Vr in both cases, we'll call this a step graded, and this we will call as linearly graded. What you will see essentially is that they both look something like this. Obviously the curves are not the same, but they look something like this. If you really want to know the relationship between Cj and Vr in each case, and you want to know how the two are proportional, what you will actually see if you analyze, if you pick up any book on semiconductors, you will see that for a step graded junction, 1 by Cj square is proportional to Vr, and in this case 1 by Cj cube is proportional to Vr. So therefore, if I now were to take these junctions, what we will see is, or rather I should say 1 by Cj square, and this is 1 by Cj cube. We will see that they will be something like this. They will be linear. Now in both cases, One case you will see that the variation in the capacitance is little bit more with respect to the same VR as the other. I leave that to you as an exercise. But the point is, what are some ways in which we can increase the capacitance variation? The CR or the capacitance ratio is quite low. So there exists some kind of diodes whose doping is neither step graded nor linearly graded. Those kind of doping is called as hyper abrupt doping. Which are essentially some kind of mathematical functions of the distance x. Of course, there are many kinds of doping which are not step or linear. One of these examples is the hyper abrupt doping. And this kind of diodes are called as Varactor diodes, also called as varicaps. Varicap means variable capacitance. So, why this varactor was made? This varactor was made essentially to control the change in capacitance over a large range. These have much higher CR as compared to other kinds of diode junctions, other kinds of PN junctions. Now, we will not get into the details of hyper abrupt doping. That is actually a course on advanced solid state devices. So, we will look at some application of Varactor diode and why it is made. The reason the Varactor diode was made was to control the resonance frequency with respect to the reverse voltage. So essentially what we want, if the resonance frequency is F0, then it must be proportional to VR. This was intended. That the resonance frequency should be directly proportional to VR. So therefore, as you know, the resonance frequency is nothing but 1 by under root L C. So here if you replace this C by Cj, you will see that this is proportional to VR. So if L is constant, what you will see is 1 by root Cj is proportional to VR. So therefore now if you draw a graph of VR with respect to 1 by Cj raised to half, you will see that this is linear. This is very important to control the resonance frequency, and that too for a higher Cmax to Cmin ratio. This is what is called a Varactor diode or a varicap, and its symbol is like this, which indicates a diode plus a capacitor. Now, Varactor diodes are extensively used in oscillators. Oscillators, because their resonance frequency can be changed, so therefore you can generate any RF frequency of your choice over a broad range of frequencies. So simply by having a circuit like this, if I have, let us say I have a resonance circuit where, let us say I have a parallel resonance, I have R, I have L, and I have a variable C. I have a variable C. Then in that case I can use a Varactor diode. One way to do that is the following. So all you need to ensure is that the Varactor diode is reverse biased, and that you can do by connecting a voltage source this way. So we will call this as VR. This is a very simple example of a tunable resonator. Tunable resonator. Now we will also look at one last kind of diode that is used in RF, and that is called as a gun diode. It is named after a person called as J.B. Gunn, a British physicist who discovered this effect in the diode. Except that the gun diode is not really a diode. All the diodes that we have seen so far, they are all some combinations of P and N or metal and N, something like that. But the gun diode is not exactly a diode. So what it looks like is this. It has 3 layers. This layer is N+. What it means is that it is heavily doped with N-type carriers. The third layer is also N+. These two are identical. But over here in the middle, it is N-, which means it is lightly doped. N- is lightly doped. Now, what happens is, because the N+ carriers are there in abundance, the depletion region, again, because they are similar type of semiconductors, the depletion region is not there. So therefore, if I were to apply some potential across this, what I would see is that if I were to draw an IV characteristic, this will start conducting almost immediately. And the electrons will flow in one direction and the current will be generated. So essentially what happens is that the current essentially peaks at one point of time. After that, something very strange happens. After that, something very, very strange happens. And that is what is called as the gun effect. The gun effect essentially shows that once the device, this kind of devices, they start conducting in large number. If you remember, all semiconductor devices work on the principle of energy bands. You have something called as Fermi level, you have something called as the valence band, you have the conduction band. So up until here, the electrons in large number, they are in the conduction band. But then, once the conduction is very high, if you start increasing the voltage, the bias voltage across this, I call this as V and this I call as I, then the N- region starts playing a role. What it does is that it effectively causes a phenomenon where the energy level of the electrons in the conduction band, which are already free, that increases. Now therefore what happens, the effective starting of the conduction band also increases. Therefore it makes the next electrons, after increasing V further, difficult to go into the conduction band. And then what happens is that the current starts dropping. This is something that you would not expect in a normal diode. This is called as the gun effect region. But what this is indicating? This is indicating that if voltage is increasing, the current is reducing. This region also indicates negative resistance. And the moment you have negative resistance, you can use it not just to consume power, but to generate power. So therefore, this gun effect is used in oscillators. Used in oscillators and synthesizers. Or rather, at one point of time, they used to be used like this. These days, we have much better synthesizers available, so the gun diode is slowly phasing out. But in case of high power applications and some other dedicated applications, the gun diode is quite important. Its symbol essentially looks like this. So it's not actually a diode. Such kind of devices which are able to, such kind of solid state devices which are able to exhibit this negative resistance, that is where the I and V are inversely proportional to each other. These kind of devices are called as transferred electron devices or TEDs. So in the last lecture and this lecture, we looked at broadly 4 categories of diodes. We looked at the pin diodes, which are used for switches. We looked at Schottky diodes, which can turn on and off very easily, but they are not used for switching as such because they conduct more in the reverse bias. But Schottky diodes today, what we saw was able to exhibit lower built-in potentials and lower reverse recovery time, which make them ideal for use in low power detection and in places where the on and off has to be very quick. Next, we took a look at something called as a Varactor diode, where we can actually use the reverse bias voltage across the diode to control its capacitance, the junction capacitance, and that too in a pretty large range thanks to something called as the hyperabrupt junction doping. And the last but not the least, we saw what is called as a gun diode, which is able to exhibit negative resistance at one point of time, and therefore it finds extensive use where the waves, the RF waves, need to be synthesized. So we shall continue in the next lecture by discussing other RF devices as well. Thank you.